Hello everyone. I hope you had a very fantastic day of learning yesterday. Today we will continue our exploration of microcontrollers by diving into the basics of microcontrollers. Get ready to expand your knowledge and discover the fundamental building blocks of these incredible devices. So today we are going to explore the performance factor that plays a vital role in selecting the perfect microcontroller for your applications. So let's get started. So today we are going to cover these topics. First one is the automotive electronics, next one is the microprocessor and microcontroller, and how to choose a microcontroller, and top microcontroller manufacturers and board design procedures. What are the board design procedures will be there, we will discuss. First one is the automotive electronics. So what is the automotive electronics? It refers to the application of electronic system and components in a vehicles. So these electronics are responsible for controlling the various functions and systems in modern automobiles and enhancing their performance, safety and efficiency. So these cover a wide range of areas and technologies. What are the main components and system includes means the engine control, that means electronic control unit. So this is a brain of the vehicle. It responsible for controlling the engine's function such as the fuel injection and ignition timing and emissions like that. Next one is we all know that ADAS. So what is the ADAS? That means advanced driver assistance system. So the system uses some sensors, cameras and radar to assist drivers in various ways. Examples include the adaptive cruise control and lane departure warning and blind spot monitoring and automated emergency braking like that. Next one is the infotainment system. So these infotainment system provides the audio, video and navigation functionality into the vehicle. So include features like touchscreen display and GPS navigation, Bluetooth connectivity and smartphone integration, and some entertainment options will be there. Next one is the powertrain electronics. So these includes electronic components and systems involved in managing the powertrain, such as the transmission control modules and traction control systems and electronic stability control. Next one is the main one, that is a safety system. So the automotive electronics plays a very crucial role in ensuring the safety of occupants. So this includes like airbags, anti-lock braking system and electronic brake force distribution and electronic stability control like that. ESC, electronic stability control, in the sense that means ESC. So these integration of electronics in automobiles continue to grow as the vehicles become more advanced and also the connected. So this is a very essential for overall operation of efficiency and performance of the electric drive train also. Next one is the embedded system. So what is the embedded system? Do you know have any idea about that? What is the embedded system? So do you have any idea about what is embedded system? I will tell you. Embedded system, in the sense it refers to the computer system design to perform some specific functions within a larger system or a device. It is a combination of hardware and software components that are tightly integrated to perform some dedicated task. Okay, this is the embedded system. Next one is what is the purpose to build embedded system? So these are designed with some specific purpose or a function in mind. So they are tailored to meet some requirements of the application or a device they are embedded in, or rather being general purpose computing devices. Next one is embedded system typically consisting of tightly integrated software and hardware components. So hardware includes microcontroller or microprocessor, memory input or output interfaces and other peripherals. So the software, in the sense, it often referred to as a firmware, is specifically developed for the embedded system and is responsible for controlling its operation. What are the examples of embedded system? So it includes a home appliances like a washing machine, refrigerator and micro ovens, and consumer electronics like smartphones, digital cameras and televisions. Automotive system like ECU units, infotainment system, ADAS, advanced driver assistance system, like that. So these are all the embedded system applications. So here you can see one block diagram. So it includes some sensors and actuators and displays and operator and clock. So these are integrated within the embedded system. Next one is the airbag system. So what is the airbag system? So airbag system in electric vehicles is a safety feature. The safety feature designed to protect occupants in the event of sudden deceleration. It consisting several components that work together to detect a crash and deploy airbags to help the potential for injury. So here is an overview of the how the airbag system is in an electric vehicle, typically the function. So first, airbag control unit. So that means a main microcontroller unit. So there's a So airbag control unit. So this airbag control unit as a central control module for the airbag system. It receives the input from a crash sensor. So here you can see the weight sensor and radar sensor, like that. So it receives the input from the crash sensors. If a crash has occurred means, and if airbag deployment is necessary. The AC utilizes some algorithm to to analyze the sensor data and make a rapid decision. So next one is the airbag model. So here you can see the one airbag model. So the EVs are equipped with various airbag models located throughout the vehicle. So common location include the driver steering and passenger side dashboard, side panels, curtain airbags, like that. Sorry for the interruption. So each airbag model contains an airbag cushion made up of a lightweight and tear resistance material also, such as a nylon. So when deployed, the cushion rapidly inflates with gas to provide a cushioning effect and prevent occupants from impacting the hard surface. Next one is the pretension system. So what is the seat belt pretensions? In many modern electric vehicles, including hybrid electric vehicles, the airbag system is integrated with the seat belt. Seat belt pretensions. So these devices activate simultaneously with the airbag deployment to remove excess slack from the seat belt webbing. So by tightening the seat belt pretensions, help keep occupants securely restrained and in the optimal position for the airbag's protective function. So it's important to note that electric vehicles employ safety system beyond just airbags, such as a electronic stability control unit, that means ESC, and anti-lock braking system ABS, and advanced driver assistance system ADAS. So these system works in conjunction with the airbag system to enhance overall safety during the various driving conditions. So this is our airbag system. And next one is a one block diagram. So what is a block diagram? It will give the information means first one is the input output. So these input output handles communication between the microcontroller and also the external devices such as the sensors, actuators, displays and other peripherals. It provides means to receive the data from the external world, outside world, and send data to the external device as output. So it is consisting of various pins or ports that serves as a communication interfaces for connecting to different devices. Next one is the central processing unit. So this is a brain of the microcontroller and carries out the data or instructions and calculations necessary for the system's operation. It performs tasks such as the fetching instruction and decoding them and executing operations and controlling the flow of the data. It includes like a ALU, that means arithmetic logic unit, and control unit, and registers that holds some temporary data during the processing. Next one is the data memory and program memory. So we all know the data memory and program memory. So program memory in the sense is also known as a flash memory or a read-only memory. Okay, it stores the some program instruction that the microcontroller executes. So it contains some machine code or compiled instructions that define the behavior and functionality of the microcontroller. Next one is the data memory. So this is a random access memory. We can say that RAM is used to store the temporary data during the program execution. It is divided into 4 different sections such as a stack, a heap, and variables. So mainly the CPU uses the data memory for storing and retrieving the data record for the calculations and immediate results and variables used by the program. So these components work together to enable the microcontroller to perform its some critical functions. So the CPU fetches instructions from the program memory and performs some calculations and operations using the data memory and communicates with the external devices through the input-output model. So this will explain the block diagram of the computer essential. Next one is there are 2 instruction sets will be there. So first one is the CISC and RISC. So CISC in the sense that means complex instruction set computer, and RISC in the sense reduced instruction set computer. So what is the difference between the CISC and RISC means? So first one is a CISC. That means a complex instruction set computer is in one kind of the architecture and instruction set design that includes inclusion of the some complex instruction capable of performing the multiple operations in a single instruction. It is a one kind of the processor typically have a large and varied instruction set and including instruction with some various length, variable length. So these CISC instruction set can perform some tasks such as a memory access and arithmetic operations and logical operations and complex data manipulation. Next one is a RISC. So examples of the microprocessor architecture that follows the CISC instruction sets in the sense of Motorola 68000 and DEC VAX like that. Next one is a reduced instruction set computer. This is one kind of the architecture and instruction set that focuses on simplicity and regularity and the execution of the small number of the simple instruction. So these processors have a limited set of instruction typically with a fixed length and that performing some basic operation only. RISC processor tends to favor a simpler and more streamlined design and allowing for the faster execution and more efficient use of the hardware resources. So these instructions typically execute in a single clock cycle which improves performance but may require more instruction for the complex task. So examples of the RISC. What is the example? Include ARM and MIPS and PowerPC like that. Next one is the volatile memory. What is a volatile memory? So it refers to type of a computer memory that requires a constant power supply to retain its data. When power is removed or lost, the contents of the volatile memory are erased or lost. So this is for random access memory. It is a common type of volatile memory. It is used for storing the temporary data during a program execution as well as the variables and steps and hacks. Next one is the non-volatile. So this is a one kind of the computer memory that retain its data even when power is removed or lost. Non-volatile memory is used for storing the permanent or a semi-permanent data such as a firmware, program instructions and user data that needs to persist across the power cycles. Next one is the architecture. So here there are 2 architectures. So one is a von Neumann architecture and hardware architecture. So these are the very 2 fundamental computer architecture designs that describe how the CPU and memory are structured and interact with each other. First one is the von Neumann architecture. So these architecture named after mathematician and computer scientist John von Neumann is the basis for most modern computer system. In the von Neumann architecture, program instructions and data instructions are stored in the same memory space, typically referred to as a memory or a RAM. It consists of the following components: so central processing unit and memory and control unit and data bus, like that. So in the monument architecture, instructions are fetched one at a time from the memory and executed sequentially by the CPU. So this sequential executions of instructions limits parallel processing capabilities. Next one is the hardware architecture. So these hardware architecture, named after the Hardware University Automatic Sequence Controlled Calculator, that means ASCC, is an alternative to one human architecture. In this architecture, the program instructions and the data are stored in the separate memory space, typically refers to as the instruction memory and data memory. It consists of the following key components. First one is the instruction memory, data memory and program memory, CPU, and one control unit will be there. So this architecture allows a simultaneous access to both the instructions and data memory, enabling parallel processing capabilities also. This can lead to potential performance advantages in certain scenarios, especially for the applications that require frequent data access. Next one is the microprocessor. So we all know that microprocessor is one kind of the integrated circuit. That means IC that serves as a central processing unit of a computer or an electronic device. It is a very highly complex and compact electronic component that performs the primary functions of the data processing, calculation and control within a digital system. Here is an overview of the microprocessor. It consisting of the instruction program, data RAM and transducers and keyboard scheme. This is for the communication purpose. Arithmetic and logic unit control, instruction set will be there, and clock speed will be there. So these are all the main components in the microprocessor. The next one is the microcontroller. So this is one of the compact integrated circuit that combines a microprocessor core, memory and input-output peripherals on a single chip. It is specifically designed to provide control functions interface with the other electronic components in an embedded system. So it consisting of the CPU and UART, program memory, timer memory, parallel port will be there, input-output peripherals will be there, timers and counters also, interrupt handling also will be there. So microcontroller have interrupt capabilities to respond to time critical events or external stimuli. Next one is so these are widely used in various applications including home automation, robotics, automotive systems, industrial automation, medical devices, consumer electronics and more. So here, how to choose a microcontroller for a different application. So first one, application types. What are the application types will be there? So while choosing a microcontroller for the different types of applications such as a standalone, real-time and network application and mobile application. So standalone in the sense determine the specific requirements of the standalone applications including the desired functionality, processing power and memory and input-output requirements. So evaluate the microcontroller's capability to meet those requirements such as its processing speed and available memory and efficient input-output pin also. So considering the power requirements and whether the microcontroller should operate in a low power modes to maximize the battery's life or minimize the energy usage. So this is for the standalone application, and next one is a real-time application. So first identify the specific real-time requirements of the application such as some strict timing constraints, deterministic behavior and rapid response to those events. So choose a microcontroller with a high clock speed and efficient processing capability to meet the real-time demands. Next one is a network application. So determine the required network connectivity such as the Ethernet and Wi-Fi and Bluetooth or other protocols. So we have to choose a microcontroller that supports a required network interface or has a capability to interface with external network models. So these evaluate the microcontroller processing power and memory to handle network communication protocols and data processing requirements also. So consider the availability of the software libraries, drivers and middleware for networking protocols to simplify the development. So mobile application in the sense such as the power efficiency, compact size and compatibility with the mobile operating system. So choose a microcontroller with low power capabilities and optimize the energy consumption to maximize the battery's life. Next one is the types of embedded system. We know that small scale and medium scale sophisticated embedded system. Next, there will be the one selection process will be there. So what is the selection process? We have to choose a 8-bit or 16-bit, 30-bit. So whatever you want, we have to choose it. Next, we have to select the microcontroller memory also, and resolution bit we have to check, and the speed of the microcontroller. So these are the point will be while we selecting the microcontroller, we will check once. Next one is the top 10 microcontroller manufacturers. What are the company to manufacture the microcontroller for, especially for the EV? So as of my knowledge, these are the manufacturers that provides microcontroller for the EV. That will be the NXP, Trans Semiconductors and Microchip and STMI, Infineon, Texas and Cypress Semiconductor, Analog Devices like that. ROHM Semiconductor. So these manufacturers have a very strong presence in the automotive industry and offer microcontrollers specifically designed for a EV application. Next, we will take it as a Texas Instruments. From Texas Instruments, we will take it as a one famous C200 microcontroller is especially used for. This is a very popular microcontroller. Popular choice for electric vehicle application due to its high performance capabilities and robust feature sets. So it has power processing power. So the C2000 microcontroller features powerful 32-bit floating point DSP. That means a digital signal process core. So this DSP core coupled with a high performance CPU enables efficient computation of the complex control algorithms required in EV applications. The advanced architecture of the C200 microcontroller allows for a simultaneous execution of control loops and motor control algorithm and other real-time tasks with minimum latency. Next one is it has a C200 microcontroller in motor control applications which are very crucial for a EV propulsion system. So this provides dedicated peripherals such as a pulse width modulation modules and high resolution ADC and position and sensing interfaces and specifically designed for the precise motor control. So these are all the very popular in microcontrollers from the Texas Instrument, especially for we are making the electric vehicle. Next one, the C200 device family and the performance ranges with the various microcontrollers. So example application single phase onboard charger, single high voltage motor. In this we have to use these microcontroller. And speed 400 to 800 MIPS means we have to use these microcontroller device family from the C200. And next one, so comparing the cost of the different types of the microcontrollers, we have to choose a system on chips and digital signal processing and FPGA. So can be complex and depends on various factors such as functionality and performance and volume production. So as a low cost will be the microcontrollers. Though microcontrollers are the most very cost effective option among these listed options because can vary based on factors such as the architecture performance, features and memory capacity and peripherals. Basic 8-bit or 16-bit microcontroller can be relatively inexpensive, suitable for simple applications with low processing requirements. Next, this FPGA, these can be figured have a higher cost compared to all of this, because the cost of the FPGA varies significantly based on the factors such as the size, number of logic elements, performance, input-output capabilities, and other complexity design. Next one is how to design a microcontroller target board. So here you can see the designing the microcontroller target board for an electric vehicle involves several steps. We have to select the right packages. So these are the package types. So DIP and QFP and SOIC, PLCC, BGA. First we will define the requirements. So clearly define the requirements and specification of your target board, considering the factors such as the specific EV application, design features and performance requirements like that. Next one we have to select the microcontroller. Next we have to create the schematic diagram also. So these are the process selection criteria, and we have to develop the tools and number of input outputs, performance, cost and hardware tools and power consumption, all they will be there. These are the design flow. So first one we have to create the schematic design for your target board, including the microcontroller and power supply circuitry and voltage regulators and decoupling capacitors and other components. So these schematic design then flow into the layout. So then go into the layout design. After completing the layout, so translate the schematic diagram into the layout design using appropriate PCB design software. And next, prototype and testing. So at last we have to conduct through testing and some verifications of the board's functionality, including the functional testing of all the interfaces and peripherals and communication protocols. So these are the hardware design flow. And next one is a schematic design consideration. We have to use a schematic design consideration by using the PCB schematic software. And next one is that we have to create a layout from the schematic. So first we will check the footprints and placement of components as per the schematics, and placement of footprints as per the components placed in the schematics. Next one is the length matching and avoid the right angle traces. Place a high speed memory close to the processor. So these are all the points while we creating the layout design for our target board. So this is a software design flow. So first we have to write the code and translate the code into the machine operating codes. Then we have to debug the code once, and next we have to next step will be the emulation hardware. What is the emulation? Do you have any idea? Do you have any idea about that emulation? So emulation of hardware means it's a very crucial role in the microcontroller development cycle, especially for verifying the debugging the software on simulated hardware platform. So it involves some using the specialized tools or development boards that emulate the behavior of the microcontroller hardware. So this enables yearly testing and debugging the software without the need of the physical hardware. So this is the emulation hardware. So this is the overall microcontroller development cycle. This is a simulation. This one for evaluation. This is for emulation. So thank you all. We will see in next class.